Hi class, we are now on chapter 4.3, the nuclear atom. We're going to be discussing the atom and the history of what we know about the atom has come to be. So an atom is the smallest particle of an element that retains the characteristics of an element. I know I'm repeating myself, but hopefully this is sticking. We cannot see atoms with our naked eye. By the 19th century, scientists already knew or were convinced that matter was composed of atoms, and at the time, they believed that it was permanent, indestructible building blocks that everything was made of, meaning the atom was the smallest particle, nothing was smaller, and you could not break it. That was it. When you got to an atom, you were done. And I mean, if you look at gold, you could go into layers and layers and layers till you start getting to atoms, till you get to that one last atom, and that's it. You cannot go any further. So J.J. Thomson comes around, and through his research, he creates this, what is called the plum pudding model. And it's stated right here. What he believes is that there are an existence of protons and electrons. Protons and electrons, let me explain. He had an idea that an atom was created of protons and electrons. And he calls it the plum pudding model. I'm guessing that was a food that was common back then. I don't know what plum pudding is. I like to call it more of a chocolate chip cookie. That might be a ball. So cookie dough ball. And what it's made out of is the dough would be the positive charge, the positive matter. That's very positive. Electrically charged, and then scattered out would be these chocolate chips that are called electrons, and these electrons are negatively charged. So with the positive matter and the negatively charged particles, I talk way too fast, they balance each other out and giving neutral existence for these atoms. So the positive and the negative cancel out, even though one is still negative and one is positive. So he discovered the existence of an electron. So this is where this plum pudding model came, that all the pudding is positive matter, and there are electrons scattered out randomly, and they are scattered in this matter, and they neutralize the atom out by being negative. So that's what he said. He proposed that atoms must contain positive charge that balances the negative charge, which overall makes this atom neutral. So Rutherford comes along, and he understands Thomson's plum pudding model, which is made up of protons and electrons. Protons being positive, that's the positive pudding there. That's the fancy name for it. And then the electrons are negative, and they are scattered. They're called plums. I call this chocolate chip cookies, and a chocolate chip in the cookie. And they are what balance out the positive matter. So these small little spheres of negative electrons are scattered out through this pudding mix matter. Okay, so what Rutherford, he decided to test what he believed, his information based on J.J. Thomson's plum pudding model. And what he did is that he took these tiny particles called alpha particles, and they were directed at thin sheets of a gold foil. Gold foil is made up of strictly gold atoms. And what he proposed would happen was that because there's more positive matter and not as many, think of chocolate chips in a cookie, these alpha particles will go straight through the pudding like nothing. They will just keep going at high speed and go straight from one end to the other end and carry on through. That was his expectations of this. That was his hypothesis. He thought that that's what was going to happen, and he tested this out. So if the plum pudding model was correct, the alpha particles would pass right through the gold foil with minimal deflection, meaning when those alpha particles did come into contact with an electron, because there were so few electrons or chocolate chips in a cookie, there would not be a big impact. There would maybe have one deflection or one that might be hit at an angle, but the majority would go straight through with minimal problems. But what happened in the Rutherford's gold experiment is that's not what happened. He actually did get a small number of alpha particles that were deflected at an angle or even bounced back right where they came from with force. So that was something unexpected, and Rutherford had to look at what his results were to try to figure out what was going on. And what he he made a statement. But what he did is that based on his experiments and what he came up with, he had a statement about the nuclear theory of an atom. And based on his research, these are the three things he came up with. Most of the atom's mass and all of its positive charge is contained in a small core called a nucleus. So no more is there a plum pudding of where it's just like a chocolate chip and electrons. What he's saying is that, see this yellow, this is the atom. That it's very dense. This is called a nucleus. And in the nucleus is where most of the atom's mass and all of the positive charge, which would be protons, is contained. So everything is concentrated in this one little part, even though this atom is way bigger than what is in the center. So he called this the nucleus, and he decided that protons were, we haven't really discussed neutrons yet, but protons were in the center, and they created most of the mass for this atom. Most of the volume of the atom is empty, through which the tiny negatively charged electrons are dispersed. So what he proposed is that even though there's a real tiny center that's completely concentrated, and that's where most of the mass is, there's still an outer layer, and that's where the electrons, the negatively charged electrons, are. The number of negatively charged electrons outside the nucleus is equal to the number of positively charged particles, called protons, inside the nucleus. This makes the atom electrically neutral. So for the amount of protons you have in the center, you will have the same number matching of electrons on the outside of this layer. So let's say if we have 3 protons in the center, you also have 3 electrons to balance out the positive charge. So that's what this is looking at. The nucleus is greatly enlarged, and the electrons are portrayed as particles outside. The electrons are dispersed throughout a large volume, but weigh almost nothing. So that's the other thing. Protons have mass to it. Electrons are so small that they have literally no mass. It's almost negligible, because it's probably like 0.00023 zeros and then 1.5. So it's so small that they consider them massless. So the dense nucleus makes up more than 99.9% of the mass, but occupies only a small fraction. Okay, the electrons are distributed through a much larger region, but don't have much mass. So when you look at this atom here, there is a very concentrated center, and then there's a huge outer layer. The way to explain this, to make you understand how concentrated the nucleus is, where most of the mass is, and how big the outer layer is. Think of a golf ball or a ping pong ball in the middle of a professional football stadium on the 50-yard line. I think it's 50, right? Is it 50? I used to know. But it's in the center of the field. That is the nucleus. That little ping pong ball or that golf ball is where all the mass is. And everything else in the football stadium, including the parking lot, is where the electrons are located. The outer layer is massive compared to the concentrated center, and electrons are out there, but they don't weigh. We consider them massless compared to the protons that are in the center. So the nucleus is very dense, and the volume is very, very small compared to the rest of the atom. So that's how different this is, and how much more room the electrons have. They have empty volume, is pretty much what it's called. If matter was composed of atomic nuclei piled on top of each other like marbles, it would be incredibly dense. So that's what you can think of this as, is marbles here, and then everything else is just empty mass with maybe a few small particles that aren't even as big as marbles, something even smaller than that. And that's it.